In this video, I will start with talking about the fact that communication channels are varying both over time and frequency, but we can divide the time-frequency resources into what we call coherence intervals, which are small enough so that the channel is approximately constant in both time and frequency. Then, in order to understand how we can communicate in each coherence interval, we will shift focus and talk about massive MIMO. It's a type of multi-user MIMO with specific properties. We will talk about its background and motivation, and we will talk about duplexing modes that can be utilized to communicate using the coherence intervals, and we will finally define this uplink system model. The first thing we will talk about today is whether or not a communication channel can be viewed as a linear time-invariant system. So a system is something that takes an input signal and produces an output signal. So a channel is in that sense a kind of system. However, the type of systems that are generally analyzed in signals and systems classes are the linear time-invariant systems, or LTI. And the question is a wireless communication channel a LTI system or not? So if x of t is the signal that we are transmitting, and this is the wireless channel, and y of t is the received signal, is this relation here described by a linear and time-invariant system or not? Because that is what is required in order to talk about Fourier transforms and these type of things that are used to analyze systems. And there are two parts, the linear and the time-invariance. And the linearity is something that is guaranteed by Maxwell's equations. However, the time invariance is a much more complicated thing. And that is because as soon as either transmitter or the receiver or something in the propagation environment is changing, well, then we have lost our time invariance. So a wireless communication system is generally not time invariant. However, we can zoom in at a particularly short period of time, and then we have an approximate time invariance. And the coherence time is representing that. That is the time that the channel is approximately time invariant, and where we can utilize everything that we know about signals and systems in order to analyze this type of channel. And one can build different types of models of for how long time period can we view the channel as being time invariant. And one typical way of doing that is to say that this coherence time, Tc, is lambda, the wavelength, divided by 2 times v, where v is the speed at which we are moving. So it's sort of saying that how long time does it take for us to move half a wavelength. However, when the transmitter or receiver have moved half a wavelength, then the channel can have changed substantially. So it could be good to be more conservative, for example, measuring the time it takes to move a quarter of wavelength, or even shorter distances than that. But the important thing here is not the exact number, but how it is behaving in general, and that is that the coherence time is proportional to the wavelength, which means that as we go up in frequency, the wavelength becomes shorter, and so does the coherence time. And it's also important to notice that the coherence time is inversely proportional to the speed v at which we are moving, either transmitter or receiver. If we are assuming now that we are operating within the coherence time, well, then we can analyze this channel from the transmitter to the receiver as a time-invariant system. However, there is still another important property, and that is whether this channel or system is time dispersive or not, which means that if you transmit the signal, will the signal be spread out in time or not? And some dispersion is quite natural in wireless communication because you have typically multiple propagation paths with different time delays, which is then spreading out the signals over time. However, if we are looking at the frequency response and the absolute value of it, then we can see here is a particular channel with 5 multipaths where, as you're changing the frequency, you see some substantial variations. But if we are zooming in at a sufficiently small interval of frequency here, then we can say that this frequency response is approximately constant. And why is that important? Well, we call that the coherence bandwidth, and that is the bandwidth over which the frequency response g of f is approximately equal to a constant. And that means that if we are going back to the time domain, well, then the response of this channel, g of t, is going to be that constant multiplied with a direct delta function. And that means that to represent this channel, the only thing we need to know is one complex valued constant. And the coherence bandwidth is also something that varies a lot depending on different scenarios. And you can also see in this example here that sometimes we have rapid changes and sometimes we have less rapid changes. So if we just want to have a simple model, then we can say that the coherence bandwidth is equal to the speed of light, c, divided by the distance of the maximum propagation delay. And then we subtract d min, which is the shortest propagation path. So this is the delay spread, is something that's describing that at least. And if we think that that is creating too large variation, we can be more conservative and say that the coherence bandwidth is only half of what we described over here. But the important thing here is not the exact model, but to get a feeling of how it works. And that is that this is something that is inversely proportional to the path length difference. So now we have defined the coherence time and the coherence bandwidth, and together they are defining a coherence interval. So we are communicating over time, and we're having a certain amount of bandwidth. And this bandwidth we are chopping up into different pieces so that each of them have a width that is equal to the coherence bandwidth. And then over time, we are dividing up our communication into intervals that is matching with the coherence time. So within one coherence interval here that is spanned by the coherence time and the coherence bandwidth, we are having a constant channel that is also described by only one scalar. This is describing the channel between one transmit antenna and one receive antenna. Now, according to the Nyquist channel sounding theorem, we can figure out how many times we can use this channel within a coherence interval. So since the bandwidth is BC, we need BC complex samples per second to describe a signal that goes into something like this. And since the time period is TC, then BC times TC is the number of complex samples within a coherence interval like this. And we can also call this complex symbols. We have now defined what is known as the block fading model, where we know that the channel is changing over time and frequency, but we divide the time frequency resources into coherence intervals, which are a block of time and frequency such that the channel is time invariant and described by a scalar. And in this way, we will break down the operation of the communication system into these coherence intervals. Within the coherence interval, we need to learn how the channel behaves, send data, and then we repeat it again over different coherence intervals being located in time and in frequency. And we can view this as being a multi-carrier system, where each of these coherence intervals representing one subcarrier or one set of subcarriers. So this is really an example of a fast fading channel that we considered earlier in this course, where we were talking about the ergodic capacity as being the performance metric. And then if we are counting different coherence intervals, each of them is providing one channel realization. And we are then, when we are talking about ergodic capacities, coding information over a very large number of coherence intervals. So one interesting question is, how large is a coherence interval in terms of the number of symbols that fits into it? Let me give you an example of that. We would like our users to be able to move at a typical vehicular speed in a suburban area. So say that the maximum speed that we allowed for is 30 meters per second, which represents like 108 kilometers an hour, for example. And say that the difference between the longest and the shortest propagation path is as much as 1 kilometer, which could happen in the suburban area when you have reflection that's coming from far distances. Then, if we're using a typical carrier frequency of 2 GHz, which means that the wavelength is 15 centimeters, then we can compute the coherence time and the coherence bandwidth using the formulas that I described previously. So the coherence time Tc was the wavelength lambda divided by 2 times the speed at which we are moving. The wavelength is 0.15 meter, and we have 2 times 30 meters per second. And if we compute this, we get 2.5 millisecond. So the coherence time is around a millisecond, a bit more in this case. And the coherence bandwidth, BC, is the speed of light divided by 1000 in our case. So here we have the speed of light, 1000, we get 300 kilohertz, that's our coherence bandwidth. And that's also typical, a few hundred kilohertz, that is typical coherence bandwidth. And if we are multiplying 2.5 milliseconds with 300 kilohertz, we are getting 750 complex samples that we can send within one coherence interval. If we are using those more conservative ways of computing the coherence time and coherence bandwidth, so we are dividing by 2 times here, well, then we should divide by 4 and we get more around 200 complex samples, which is also a very common number that people are considering when analyzing this type of communication systems. We will now use this type of models for the time-varying channels and revisit the multi-user MIMO communication that I started talking about in the previous video. So remember, we had an uplink case where we have multiple users, let's call them K users, that are communicating with a base station. So here we have the transmitting users and here we have the M antenna base station. And this is a multi-point-to-point MIMO system, so we still call it MIMO even if each user has a single antenna, while the base station has multiple antennas. And then we have the downlink from the base station to the K users, and this is a point-to multiple point MIMO, so we have multiple users that are served. The term multi-user MIMO has been around since the 90s. Before that, people were talking about space division multiple access, or SDMA, and nowadays it's very popular to talk about massive MIMO, which is a short form for massive multi-user MIMO. So conventionally, multi-user MIMO systems were considering having, say, 8 antennas and up to 4 users that were served at the same time. This is what the LTE or 4G systems have been using for some time and also being used in Wi-Fi systems. And in those cases, if we know that the multiplexing gain that we're getting in the point-to-point system is the minimum number of transmit and receive antennas, then ideally a multi-user MIMO system can provide you with a capacity gain compared to a size system, which is the minimum number of base station antennas and users, which is equal to the number of users since we have fewer users than antennas at the base station typically here. However, we seldom reach this type of gains here because it's hard to operate this type of systems in a good way in practice when we are taking all of the channel estimation into account as well. And that is something that Massive MIMO is an attempt to deal with. So in those cases, instead of having, say, up to 8 antennas, people are considering around 100 antennas. For example, in 5G, 64 antennas is considered being Massive MIMO. And Massive MIMO is designed to serve up to, say, around 10 users or so. So a characterizing feature of Massive MIMO is that we have much more antennas than users. And if you just look at the capacity gain that we can ideally achieve, that one is determined by the minimum of the number of antennas and users, which is equal to the number of users when we have much fewer users than antennas. However, there are many practical benefits of Massive MIMO that makes it possible to actually achieve this capacity gain in practice, while that is much more hard to do in conventional multi-user MIMO. So the benefits are that the channels are behaving as if there are less randomness in them, thanks to a diversity gain, and we're getting a large beamforming gain when we have a large number of antennas, and we also get less interference between the different users. And we will look more into these different properties in the following slides. So a general motivation for Massive MIMO can be achieved by looking at the sum capacity when you have 2 users, and that is something that we considered in the previous lecture. Then the rate of user 1 plus the rate of user 2 is equal to log 2 of the determinant of an identity matrix plus row uplink times the channel matrix multiplied with the Hermitian transpose of the channel matrix. And we can rearrange the order of G and G Hermitian, put them in the opposite order, and change the size of the identity matrix because that's going to give us exactly the same result. There's a matrix identity saying that. Then, since the channel matrix has a first column describing the channel from user 1 to the base station and the second column that is describing the channel from user 2 to the base station, then we can compute this product between G and G Hermitian. It will look like this. In the first diagonal element, we will get G1 multiplied with G1 Hermitian as an inner product, so it's a square norm of G1. In the same way, the second diagonal element is going to be an inner product between G2 in itself. And on the off diagonal elements, we are getting something more interesting. There we are getting G1 from one of these G matrices, and then we get G2 from the other one with a Hermitian transpose. So we get an inner product between G1 and G2, the two different channel vectors. If we put this into the capacity expression, like this, then we can see that we should take the determinant of identity matrix plus row uplink times this matrix. And when we compute the determinant, then we should first take the two diagonal elements and multiply them together. So we have the squared norm of G1, squared norm of G2, and we have the identity matrix that adds 1 to that one, and we have row uplink as well. So we get 1 plus row uplink times the squared norm of the first channel vector, plus 1 plus row uplink times the square norm of the second channel vector. And then when computing the determinant, we have something more. We are getting the off diagonal elements multiplied together, and we get the minus sign, and we had row uplink here. So we get row uplink twice, and then we get these two elements multiplied together, which is the absolute value square of this inner product between the two channel vectors. And suppose that this part here would be removed, because it's a negative term, so we get an upper bound if we take it away. Well, in that case, we just get log 2 of this expression times that expression. And remember that the log of the product is the summation of the logarithms, so we get log 2 of 1 plus row uplink times the square norm of the first channel vector plus log 2 of 1 plus row uplink times the square of the second channel vector. And the point here is that this is the capacity of user 1, this is the capacity of user 2. So in this case, where the two channel vectors are having an inner product that is 0, well then the sum capacity is equal to the capacity of the individual users. In terms of the capacity region, it's going to be a square in this case because we are not limited by interference at all. Since the two users have orthogonal vectors that are described in the channels, they are not causing any interference to each other at all. And that is something that we would like to achieve in the practical systems. Can we somehow make sure that the channel vectors of different users are going to be orthogonal? And that is one of the motivations for Massive MIMO, something that is called favorable propagation. So consider two M antenna channels, G1 and G2, and we take the inner product of them, we take the absolute value, and divide with the number of antennas. Then it turns out that this one converges to 0 as the number of antennas goes to infinity in a lot of different situations. And that means that there are less interference between the users when we have many antennas. Here are two examples of that. So we see the number of antennas is increasing here, and here we have this absolute value of the inner product divided with the number of antennas. And we have the i.i.d. Rayleigh fading case, which is the dashed line. And then we have the solid line here, which was computed using measurements at the Alcatel-Lucent site in Stuttgart. And the important thing here is that we are seeing that as we increase the number of antennas, these inner products is going down more and more and more, which means that there's going to be less and less interference between the different users. And that happens both in the type of models that we are using in this course, namely i.i.d. Rayleigh fading, and in practical systems. And you can analyze other types of channel models and you're going to see the same effects. So why does this happen? Well, it's related to the beamforming gain and the beam width. So the beamforming gain is saying that we are focusing the signal towards the user, and the power focusing is not creating any power. It means that we are sending the signals more and more focused, we're focusing the power towards the receiver, and then less interference is going to be leaked in other directions. And that is beneficial for all the other users. As soon as they are not at exactly the same location, they are going to see less interference. Another motivating property of Massive MIMO is known as channel hardening. So let me exemplify that. Consider that we have an M antenna base station and we have a single antenna user. Towards the user we have the channel vector G. And it's complex Gaussian, have zero mean, and a covariance matrix that is an identity matrix, which means that all of the elements in G are independently distributed complex Gaussian. Then if we compute the square norm of G and divide with the number of antennas, then we can compute the expected value of it. And each of the elements here have variance 1, which means that we get m from this part that we divide by m, so the mean value is 1. If we compute the variance of the same term, it will turn out to be 1 over m, which means that the mean value is not affected by the number of antennas, but the variance is reducing. So as we add more and more antennas, the realization is going to be closer and closer to the mean value because the variance is reducing. And here's an example of that. Here we are showing the square norm of G divided with the number of antennas. And here we are showing that we are increasing the number of antennas from 1 up to 400. The red curve here is just one realization of G, and we see that in the beginning we have large variation, but then after say 50 antennas or so, we are having rather small variations, and it's starting to converge to something it looks like, and that something is 1, the mean value. So the black line here is showing 1. And if we are considering many random realizations like this and we'll compute percentiles, then 10% of the time we will be below this line here, and 90% of the time we will be below this line here, which means that with 80% probability will be in between these two different lines, and they are converging closer and closer to the mean value, so we are actually going to be very close to it in many cases when we have many antennas, which is the intention in Massive MIMO. And this is a consequence of the spatial diversity that we talked about earlier when it came to outage probabilities, for example. And there the idea was that the probability that one antenna sees a very bad or very large channel realization could be quite substantial, but when we're considering a large set of independent channel realizations, they will all start to behave in a more deterministic manner, and that was good in terms of outage probability. And here it means that the square norm of the channel vector is going to be approximately equal to its mean value when the number of antennas is large. There is also another benefit that we are seeing here, and that is that if you compute this mean value here without the normalization, it's going to be equal to m. And that is a beamforming gain, that the square norm is approximately equal to m, and that is the constant that we get when we have a large number of antennas. The name Massive MIMO is connected to its inventor, Thomas L. Marzetta, who was then working at the Bell Labs in the US, and was also awarded an honorary doctor here at Linköping University in 2015. And he was describing this concept in this extreme form in a paper called Non-Cooperative Cellular Wireless with Unlimited Number of Base Station Antennas. So he was really embracing this property that happens when you have a large number of antennas. And to take it to the extreme, he let the number of antennas become infinitely large to demonstrate that favorable propagation and channel hardening are two properties that are at its best in those cases. And Thomas Marzetta is the main author of the book Fundamentals of Massive MIMO that the rest of this course is going to be built on. Today, Massive MIMO is a main component of the 5G cellular network technology, but in 2010, when Marzetta was proposing his idea of having a very, very large number of antennas, it was considered to be very impractical. But nowadays we know that many of the properties that he was describing are also kicking in when you have a practical number of antennas around 100 or so. Here's a simplified example of the asymptotic motivation that Marzetta had in his paper. So we have a base station and two users, and we consider the uplink when the two users are sending signals xk. K goes from 1 to 2. So we have signal x1 from user 1 and x2 from user 2. We have the channels g1 and g2. And here are the elements inside of those channel vectors. And they are i.i.d. Rayleigh fading like this. And the received signal is the signal from user 1 over the channel from that user, the signal from user 2 over its channel, plus noise W, which is also complex Gaussian distributed. Suppose now that when we are receiving Y, we are applying a linear detector, A1, in the sense that we are taking in the product between A1 and Y. That gives us Y tilde 1. And this A1 is selected for user 1 based on its channel, G1, and we also normalize with number of antennas. And then A1, when we take the inner product like this, we get A1 times G1, and then we have the signal from user 1 here. We have A1 times G2 and A1 times W. And let's look at all these three different terms. Let's start with the first one, which is in front of the signal term. So we have an inner product between G1 and this linear detection vector, which is also equal to G1 with this normalization term. So this is actually the square norm of the channel vector, which is normalized. And then we know from this channel hardening property that as the number of antennas goes to infinity, this is going to approach the mean value that each of these elements are having, namely 1. So the signal term here is going to remain in the sense that we get 1 multiplied with the desired signal, x1. If we are now shifting our interest to the interfering term here, then we have a1 and g2 with an inner product. And that means that we have an inner product between the two different channels, and we multiply with 1 over m here. And then by this asymptotic favor propagation property that I talked about before, this is going to converge to 0, which is the mean value of each of the elements in this inner product. So that means that the interference term is going to vanish in the sense that we get the 0 here asymptotically multiplied with the interfering data signal. And if we are shifting our attention to the noise term here, by the same reasons, we have an inner product between a channel and noise term, and they are independent of each other, and it's the same type of distribution as we were having when we talked about favor propagation, so this is also converging to 0. So asymptotically, we are going to get a noise interference-free communication because we get 1 multiplied with the desired signal plus 0 plus 0. So the received signal is converging to only the desired signal as the number of antennas goes to infinity. So that means that we can convey a large amount of information because we have a noise interference-free communication, which is never happening otherwise. But one important challenge that is appearing in the Massive MIMO system, or actually in any communication system, but particularly Massive MIMO, is that we need in every coherence interval to learn the communication channels, to learn these channel responses, the G-vectors. So let's look more in detail on that. So we have k users, which m length channel vectors. So in total we have m times k coefficients to learn in each coherence interval, and all of them are complex valued. Then how do we learn something like this, which is unknown to start with both at the transmitter and at the receiver? Well, the basic principle is to send known signals, known as pilots. This is something that the transmitter and receiver have agreed upon in advance. I'm going to send you this signal over the channel, and then you look at what you are receiving, and from that you can deduct what the channel is going to be. And when you have a very large number of coefficients to learn, it's important to think carefully about how you design your way of sending the pilots. So if we have one antenna on one side of the link and multiple antennas, say M on the other side, then if we let that single antenna on one side send one pilot signal, then it's going to be simultaneously received at all of the receive antennas, which means that from just one pilot we can estimate all of the channel coefficients, G1, G2 down to Gm from one pilot. If we are instead doing the opposite, so we let this array with antennas send pilots, then we need to send from one antenna, then from the next one, then from the next one, and so on, in order for this single receive antenna to observe each of the different channels in a non-overlapping fashion. So if we have M antennas, we need M pilots to learn the channels. So in general, it is the number of transmitting antennas that we would like to learn channels from that determines how many pilots that we need to send. 1 or M. And that guides us when it comes to what is known as duplexing, which means that we have time frequency resources and we want to use them both for uplink and for downlink. And there are different ways of dividing the resources between the uplink and the downlink. One of them is known as time division duplex, and that means that we are separating the uplink and downlink in time. If each of these blocks here are describing a coherence interval, well then we are sending uplink and downlink within each one of them. So we are switching between uplink and downlink, and we do it fast enough so that the channel stays fixed within one of these blocks here. In order to learn all of the channels in a system like this, we can decide on should we send pilots in the uplink or in the downlink. In the uplink we have k users, so we need to send k pilots. In the downlink we have m transmitting antennas at the base station, so we will have to send m pilots in order to learn channels. But the good thing in this time division duplex or TDD cases are that we can choose between the uplink and downlink, and in Massive MIMO we have many fewer users than we have antennas at the base station, which means that we can design the system such that only k pilots are needed. The other duplexing option is so-called frequency division duplex or FDD, where some coherence intervals are used only for uplink and some are used only for downlink. So we are separating between uplink and downlink over the frequency domain. That means that every time we have a coherence interval in the uplink, we need to send k pilots, and every time we have a coherence interval in the downlink, we need to send m pilots. So the system must be designed so that it can support up to m pilots. So if we look at this example here where we have 100 antennas and 10 users, then the TDD case needs 10 pilots, so that's equal to k, and the FDD case needs 100 pilots because that is the value of m here. And if each coherence interval is containing 200 symbols, well then the FDD case is going to be consuming half of them just for pilots, while the TDD system is only using 10 symbols for pilots out of this 200, which means that it's only 5%, so it's almost negligible. So TDD operation is key in order to make Massive MIMO work. In order to have a large number of antennas, we need the amount of pilots to be not increasing with the number of antennas. So that's why TDD operation is going to be assumed in the rest of this course. So if we are operating a TDD Massive MIMO system, how does it work? Well, we take our time frequency resources and we are dividing them up into these type of frames that are matched to the coherence interval sizes. Or actually not to every single user, but typically we are deciding that we would like to support a certain dispersiveness of the channels, a certain movement of the user, and that is defining the smallest size of the coherence intervals that we would like to support, and that is then the size of the frames that we are considering. So we are taking the smallest coherence time and the smallest coherence bandwidth, and we are creating frames of that structure, and that is also giving us the number of symbols per interval. And within one frame or coherence interval like this, we are having first uplink pilots that enables us to have channel estimation, then we have uplink data, and then we have downlink data. And then in the next frame we are doing the same thing over and over again, both over time and over frequency. And in this way we are breaking down the operation of the system into frames that we can analyze one at a time. And that's what we're going to continue doing on the next lecture. So let me just remind you of the Uplink Massive MIMO System model that we talked about in the previous video. The received signal y is m-dimensional, so you have y1 to ym. Then we have the square root of rho uplink, which is a transmit power. We have g, which is a channel matrix. It's m by k, and each column is describing the channel from one user to all of the antennas at the base station. We have the vector x, which contains x1 to xk, that are the messages sent by different users. And then we have w1 to wm, which is the noise at each of the receive antennas. And remember that the parameters are from now on normalized. So rho uplink is describing the maximum power at which we can transmit. x1 to xk have a power that's smaller or equal to 1. The channel of user k is going to be modeled by i.i.d. Rayleigh fading. So column k in the channel matrix contains these elements, and each of them are independently distributed like this. Comp is Gaussian, and beta k is describing the variance, and it's also going to be known as the large scale fading coefficient. And finally we have the noise vector w, which is normalized, so its variance is going to be 1. Let me wrap up by talking about the parameter values that you can expect in a model like this. So the maximum SNR of user k is going to be the transmit power rho uplink multiplied with beta k. And how do we model these two factors? Well, starting with the power rho uplink, it is the uplink radiated power multiplied with the antenna gains that are describing how the signals from the transmit antenna is being radiated in different directions, if it's omnidirectional or directed in particular directions in a static manner. Then, since we are normalizing away the variance of the noise, we are putting it inside of this rho uplink term. So we divide them with the bandwidth, and then n0, which is the noise power spectral density, which might be around 10 to the power minus 17 watt per hertz. Typical values that we can put into this equation is that the bandwidth B is 10 MHz, that the radiated power, say, is 100 milliwatt, and that the antenna gain, if we have omnidirectional antennas, we have 0 dBi. And omnidirectional antennas that have 0 dBi doesn't exist in reality, but in a user handset we try to build antennas that are as close to that as possible, because we cannot control in which direction the user is going to hold its phone. Then when it comes to beta k, which we call a large-scale fading coefficient, this one can be modeled using various type of propagation models, and there is not one model that's always right, but there are many models that are considered in standardization, for example, or to evaluate by simulation different types of communication systems. So in the 3GPP that are standardizing 4G and 5G, they are using a model of this following type, where we are considering a propagation distance, dk, and we take dk and divide by a reference distance to get something that is dimensionless. We take it to the power of minus 3.76, and this is then giving us how much power that we have lost at a certain distance dk. And then we would like to set a constant term here that is saying how much power have we lost at this 1 meter reference distance. And this particular propagation model should only be used when dk is greater than 35 meters, because it's created for the cases when the base station is located on a rooftop 35 meters above the ground. And some typical values for the large-scale fading coefficient is presented here. So at the minimum distance, 35 meters, with the user standing right underneath the base station, well, then we will get the beta k of minus 73 dB. So we are receiving only 1 in 20 million parts of the transmitted power. And at a 1 kilometer distance, we are down at minus 128 dB. So large-scale fading coefficients are extremely small. On the other hand, when we take the transmit power and divide it with the noise power here, we are getting a very large number. So the maximum SNR can still be in a reasonable range. In summary, Massive MIMO is a multi-user MIMO system with many antennas at the base station, serving many users at the same time and frequency. And there is no strict definition, but most people are considering TDD operation. That means that we take our time frequency resources, we divide them into frames, and we use each frame for both uplink and downlink. And we match the size of the frame to the coherence interval size, so we have a constant channel in both time and frequency within one coherence interval. And we can then send uplink pilots in order to learn the channel at the base station, and use those estimates to send downlink data back and to receive uplink data.